again, this is a work in collaboration with John Baena, Daniel Escudero, Jaiberth Porras, and Javier Verbel on efficiency HFE key generation. So, just a quick context. As we've seen, multivariate cryptography, public key cryptography based on multivariate is a viable option. There are well-established signature schemes such as UOV or Rainbow. However, on the encryption side, there's been many schemes broken, so we're left with very good attacks, interesting literature on attacks. For example, HFE was broken by a mean rank attack due to the low rank of the core map. And ZHFE tries to overcome this problem using a high rank, high degree core polynomial. One problem with ZHFE is that the key generation was extremely slow. So in this paper, we propose an efficient way to construct the keys in ZHFE. Essentially, what we do is so in ZHFE, to construct the key, you have to solve a linear system, very large system of equations. And what we do is we sort it in a way, we organize the rows and columns so that the structure, so we reveal the structure of the matrix to be almost block diagonal. And then from there, we propose a way to construct the matrix more efficiently and then to solve the system very fast. The improvement in the complexity is from n to the 3 omega to n to 2 omega. And in practice, it goes from a couple of days to just a few minutes. And I think that answers the question of Ludovic earlier. So it used to be a few days, and now it's just a couple of minutes. So I'll give very quick preliminaries, since Daniel already did most of that. And then I'll talk about the efficient ZHFE key generation that we propose. I'll talk a little bit about complexity, some few remarks about security, and conclusions. So we've seen HFE a few times now. This is an HFE polynomial. We have a finite field F, a degree n extension K, and if phi is the typical vector space isomorphism, T and S are randomly chosen affine linear maps. The public key of HFE is the composition of T, phi, F, phi inverse, and S. This happens to be n degree 2 polynomials over the small field. The private key is F, T, and S. Encryption is simply evaluating P at a plaintext x1 through xn, and then to decrypt, you decrypt one by one of each of the maps T, phi, F, phi inverse, and S. The degree of F has to be very small to be able to find preimages of F. F is a polynomial in a finite field, so you need to have a small degree to be able to use something like Berlekamp to compute preimages. And because of that, it was broken by Kibnes and Javier, because the rank of when we see this as a bilinear map, the rank of the matrix is very small. So in PQCrypto 2014, Porras, Baena, and Ding propose ZHFE. In ZHFE, instead of one, we have two core polynomials, F and F tilde. And F and F tilde have high degree and high rank. So how do we decrypt? We construct this extra function z, which has a low degree, and it is formed as by multiplying x by a linear combination of the Frobenius powers of f and f tilde plus x to the cube multiplied by a linear combination of the Frobenius powers of f and f tilde. And then encryption is still just evaluating p at x1 through xn, and to decrypt, you decrypt t, then phi cross phi, and then to find a pre-image of the core map f tilde, you use this function c to find a pre-image, and finally invert phi inverse on s. A little bit more into detail into the key generation, which is the topic of my talk. What they proposed originally was to first randomly choose these coefficients alpha 1 through alpha 2n and beta 1 through beta 2n, and then determine the coefficients of f and f tilde so that this psi function has degree less than some parameter d. This yields, as Daniel said, a nonlinear system S over K. And when you look at it on the small field, it's really just a linear homogeneous system, T, with a matrix M tilde. And then you find the null space of this matrix and pick an element there. Right? That works okay, that works fine. The problem is that the matrix is large. It's on the order of n cubed cross n cubed. And yeah, that takes a lot of time. So this is what we propose. We study the combinatorial structure of this psi function. And we find out that by reordering variables and equations of this matrix, it turns out to be almost block diagonal. That for S, but the structure is preserved when you look at it in the small field. So M tilde still has the same structure. So we propose an algorithm to find a null space of such a matrix. So at the beginning, when we look at the system of the big field, everything was chaos. We knew the matrix was sparse, but that was about it. Recall that this matrix comes from the following. So the variables are the coefficients of f and f tilde, so the a sub ij's and bi's, and their Frobenius powers. These are the variables on the system. And the equations correspond to terms of psi of degree d greater than d, small d greater than d. So each equation for 1 degree d. We're really going to look only at the quadratic part. The linear part doesn't really matter. So we propose the following way to sort the variables. Let AK be the following sets of pairs. So AK is the pairs I, I plus K with I from 0 to n and K from 0 to n minus 2n over 2. On the last one, the n over 2, you only go up to n over 2, of course. And we take the union of those sets. This is very simple. It's just, if you look at a simple example, this is with n equals 6. The set A0 is just the pair 0, 0, 1, 1, 2, 2, and so forth. A1 is A0, 1, 1, 2, and so forth. And you should be thinking about these pairs as exponents of x in the HFE polynomial. And what we want is to sort the variables according to this partition of the exponents. So for ij in AK, let's call ZH the variable, the coefficient of x to the q to the I, q to the j, and let's make h 2nk plus 1 for the coefficients in f, and 2nk plus n plus I for the coefficients of f tilde. In a simple example, what that means is we first put the coefficients of the first group, the group 0, 0 through 5, 5, and then the next ones were going to be the same group, but for f tilde, and then we jump to the second group of f, and so on and so forth. So we are sorting according to that partition. We're sorting the variables according to that partition. And why that matters? Why is that important? Well, let's define the kth part of f as the terms that come from the kth partition. If you define that, f can be written as the sum of the, from k equal to 0 to n over 2 of the kth partition of f, and so on. The linear part doesn't really matter. And then it so happens that the kth part of the L Frobenius power of f is equal to the L Frobenius power of the kth partition in f. So if you look at the coefficient of x q to the s, q to the I, q to the j in CS, it is just this. And what is important here is that all the variables are coming from the kth group. So within C0 or within C1, every single variable involved in the equation comes from a single group. So the only question left is, when do the groups mix from Z0 and C1? When do they mix? So within one Z0 or C1, there's no mixing between the groups. So the only question is when q to the 0 plus q to the I plus q to the j is equal to q to the 1 plus q to the r plus q to the t. And we have a lemma, it's much longer than this, that says exactly when that happens. But here is an example of just as one of them. So x q to the s plus q to the I plus q to the j, the coefficient in psi is simply this. And what is important here is in C0, it is just they all come from the kth group, and in C1, they all come from the k plus 1 group, which brings us to the main result. So let n, q, and d be positive integers such that q is greater than 2, r, which is the log qd, is between 1 and n over 2, and d is between q plus 2 times qr minus 1 and q to the r. So we can reorganize the matrix associated with S so that it has this form. These M0 are the equations coming from the first group, and they don't mix with anything else. M1 are the equations coming from the second group, and they mix only in one equation with the variables coming from M2. That's the same all the way down to MR minus 2 and MR minus 1. And from there on, you have two equations that mix between the groups. one comment here is that this condition is not really important. It's a little bit technical, and we put it there so that the description is simpler. But you can get rid of it and just have a little bit more strange description of the matrix. But it will still be almost block diagonal. That was over the big field. Now, when we take this to a small field, what happens? Well, I had previously like 3 slides explaining this, but I think what is important is the conclusion. Nothing, the same. We get exactly the same structure, except that one row in the previous matrix becomes n rows in this matrix. So everything scales up. That's all. Maybe I should comment on this. We can directly construct this matrix from the description on this block form. So we can construct each block at a time directly. We don't have to sort it. So the sorting happens theoretically, but doesn't have to happen algorithmically. We already can construct each block from scratch. So now the only thing that is left is how to solve such a system. And it's relatively simple. So the matrix M tilde is almost block diagonal with blocks M1 tilde through Mn over 2 tilde overlapping in a few rows. And let me show you a simple example of how to do it with 2 blocks. Let's split each block into an upper part and a lower part so that the lower part of the first one overlaps with the upper part of the second one. We find Y2 in the null space of L2. Then compute R equals U2 times Y2. And find an element Y1 such that U1 L1 times Y1 is equal to 0 minus R. It is easy to see, because the R cancels with the minus R, that Y1, Y2 is an element in the null space of M tilde. And you can iterate this through the whole matrix. Here is the algorithm. And it also tells you something else. You never have to build the whole matrix. You never have to store the whole matrix. You just build one block, compute the null space you have to compute there, and then erase it, throw it out, and move to the next one. The algorithm does just that. And a few things about the algorithm. If it terminates, it returns always an element on the null space of the matrix. Every element in the null space can be the output of the algorithm. Moreover, and more important, the distribution of the output over the null space is uniform, even with this algorithm. So we're not, this is important because we are not changing the scheme at all. We have exactly the same distribution on the key space. Though the algorithm may not terminate, in millions and millions of experiments we run, the algorithm always terminates. A few comments about the complexity. We have n over 2 plus 1 blocks, each of size 2n squared times 2n squared. Let's say the complexity of reducing one block is n squared to the omega. Then the complexity of the method is n to the 2 omega plus 1. And this compared to doing Gaussian elimination of the whole matrix is n to the 3 omega. But this is not fair. This comparison is really not fair. The matrix is sparse, so there are better ways to find an element in the null space. So we run experiments comparing a sparse linear algebra algorithm to solve the system against our new method. And these are the numbers. So for example, with n equals 32, the new method takes 67 seconds and 64 megabytes against 2,000 seconds and 3,000 megabytes of memory. And that's consistent through all the numbers. Okay, so a few remarks about security. This paper is really not about security. So what we can say is that security of the original ZHFE is not affected by the new key generation algorithm because the key is chosen under the same uniform distribution. If ZHFE is not secure, that's not our problem. But during the review process, we learned about this paper by Daniel and Ray, where they discuss, where they showed that there was a rank weakness on ZHFE. And Daniel already explained that if the Lij matrices, linear transformations are non-singular, then the Q rank of this thing is log QD plus 2. And that almost destroyed our paper because it seems like ZHFE was not secure anymore, but fortunately Daniel also proposed how to fix it. If we select Lij maps to have reasonable core rank, then the Q rank does not appear to be a weakness. That's what they say, and they actually were kind enough to give us some parameters to try it out. So what we did is, let's say, with these new parameters, can we still use this new algorithm to construct the key? And yes, our new algorithm works fine with positive core rank Lij maps. And so we can use it with the new modified scheme. Some conclusions and future work. So we have proposed a novel method to construct ZHFE keys by exposing the almost block diagonal structure of the vanishing equations system. We are able to construct the matrix faster and store it much more efficiently. We find the solutions asymptotically faster, and this turns ZHFE into something more on the practical side. Our new algorithm works with positive core rank Lij maps. And I think the interesting part in the math side of the paper is understanding this combinatorial structure of the Frobenius powers of the Q Hamming weight to univariate polynomials. And we hope this can become a tool to explore a larger family of encryption schemes where we maybe do something else there to have a larger core rank, a larger Q rank, perhaps. Also, there's room for further improvement in the efficiency of this key generation. There's a lot of freedom in these choices, and because we now know the structure of the matrix very well, we can fix some variables in a smart way so that the system is much faster to solve. So I thank you for your attention, and I take the opportunity to invite you to CryptoCode 2016. It's a summer school in cryptography in Bogota, Colombia, July 5th to 6th, 2016. So this year, we don't yet have a web page, but we have Facebook and Twitter You can find us as CryptoCo 2016. Thank you.
So you introduce you arrange again the variables, and so you can introduce a plot.
Introduce the what?
Well, you have a kind of plot matrices.
Yes.
And can you use some kind of cyclic structure to reduce the key size of the schemes?
Can you use what?
Cyclic structures, like what people did in
I think you want to use a cyclic structure on the coefficients of the HFE polynomials?
Yeah, I mean, well, you have a plot matrices, somehow you can use a cyclic structure.
Well, they have already a cyclic structure. They are actually quite structured. They have a lot of structure inside each of those blocks. They are totally not random because they... So I don't want to add more structure there. They already have plenty of structure. I have to say, I would just leave it there. So
you think you can reduce the key size?
So let me show you. This is some of the slides that I didn't want to go through. When you look at it in the small field, the matrices, the blocks have this structure. So they have plenty of structure already. Yes, I wouldn't add structure there.
So you only multiply x and x cubed in the generation project. I suppose that go to q squared, go to the third, and go to the fourth, slowly go up. Can you do something like that?
I hope so, yes. So if we want to increase the Q rank, that's the kind of thing we want to do. And that's what I meant when I said we can now explore a bigger family of encryption schemes with this understanding of the structure of this matrix. So I hope to hear proposals about that, how to do that. Yes. Yes, and that way increase the Q rank.
Yes, the Q rank is log D plus 2. So if you add, probably each time we add 1, probably increase rank by 2 again.
Yeah, that opens that door, and I think it's doable. Thank you. Okay, there's a question there.
Can you go back to the slide with the table? I think it was 20 or something. Yes, which of the parameters here are referred to 80-bit security level or something, just to get an impression?
This one is supposed to be 80-bit security, although there's always the discussion about what is the real level of security, because this is based on Grosvenor basis, and the memory just kills you. But yes, it is. I think this last row is supposed to be 80-bit security.
Okay, and the row at the bottom of the page?
Yes, also.
Okay, okay, thank you.
Thank you.
For coffee. And thanks to Daniel and to the session.